All right. So, sure. So tonight we'll be talking about theory, and there's a lot of math to it, yes, but there's other things that lead up to the math, and when we talk about discretization and whatnot, which is all important, especially it's important in all aspects. Well, the first half, the model construction phase is very important. It'll be important in the history matching, because how you build the model and how many grid blocks you use will dictate how long that model runs, depending on what software you have. We talked about that last time. So so let's get in, and remember, this is the only part of the theory that we'll be talking about this particular lecture. There will be questions on the final about this, but they're not intended to be trick questions or not, and you're not going to have to invert a matrix or anything like that. It's just, do you have a good sense of what's going on when it comes to what's behind the scenes when it comes to running a model? Let's see. Okay. So there's three major components of our modeling approach. And the first one is discretization. Then there's material balance and Darcy's law. All these things are combined in our large model, such that it properly takes into consideration fluid flow and the geology and whatnot. So we'll be going into each one of these. Now, I will make a note that this lecture and these equations I'm going to present are all based on finite difference simulation. And then basically it's one grid block versus the other, and what happens between them when you run the model. You'll see it's not just two, but there is also a finite element, and the concept is the same. The equations are different. Okay, but almost all of the simulators that we'll use for reservoir modeling, oil and gas reservoir modeling, will be finite difference. Okay, so models are composed of discretized blocks, grid cells, or discretized tank. Each tank will obey the laws of Darcy's law and material balance. The tank itself will obey material balance, and the communication between one tank and another will be governed by Darcy's law. And then we put wells inside these tanks as well. So the model itself, which when we talk about the model, we're talking about the entire whatever it is we're studying, and usually most of the time it's going to be a full field, although two of the models you'll look at in this class that you'll be running are pattern element ones. But they're composed of discretized tanks. Each tank obeys the laws of the rules of material balance in the tank itself. And then the wells, then we talk amongst each other, and I'm going to go show you the equations on that, which you've seen them before, but I'll put it into the context of the simulator. And then we do have some extensions to our reservoir model, and that is these wellbore models. We call them vertical flow performance tables, VFPs. They also might be, sometimes they call them tubing tables, but they're basically, it's a table lookup of what's the bottom hole pressure, what's the conditions in the pipe, what's the type of the size and roughness of the pipe, then what do you have at the surface if you're producing. If you're injecting it, it's still a bottom hole versus surface pressure. And then I mentioned briefly that we could link our reservoir simulation model up into a pipe sim or a pipeline facilities model. And then we could go back and forth and iterate between the two of them and have one solution that it combines both of them. It's pretty sophisticated stuff on that, but and they're expensive. I think I mentioned, the software that you have or will be using is about 50,000, but someone corrected me the other day. It's between 100 and 150,000 for one license. So it's pretty powerful. So I can guarantee you they're going to give you this long password to use it, and it won't work after this class. It's too expensive. It's for IMEX, yeah. IMEX and then Builder and all the ancillary programs that go with IMEX, yes. Okay. So let's talk about discretization. Discretization is where we divide this the model into blocks. And the two things to know when we say we're going to discretize, we discretize volume and time. Okay, so start with volume. The entire reservoir is going to be made up of all these little these grid blocks, and then each grid block properties, the properties within the grid block are going to be averaged to represent a homogeneous grid block inside the grid block. But if we have a lot of resolution to the model, then it looks like it's going to be very heterogeneous, because the rule is we have to have one thing, one property. I'll get into this: one property, one item for each of these coefficients for the individual grid blocks. But we could change that and vary in that, like we did with, you saw, we had different realizations last week where we had porosity distributed and permeability distributed, but for each grid block itself, it has to be one value. We measure these grid blocks. Yeah.
Does that mean that for each grid block cell or for block?
Yeah, grid cell.
A value for saturation, pressure, all these kind of properties.
Yeah. Yeah, it's good. And we'll get into actually the next slide. Yeah, I'll show that. So one of the things to know is that it says, we say measure in feet, meters to hundreds or thousands of feet. So, and I mentioned before that if this was a grid block, in some of the illustrations I'm going to show you, they look like blocks, but they're really more like pizza boxes. They're more, the aspect ratio is it's very thin, but large.
What happened when you reduce the number of grids? What happened when they combine each other? They have like an average?
So we'll get into that. And your question could be taken two different ways. It could be if we're upscaling, how do we upscale is one question you're asking. And that's probably the question you're asking, which we'll talk about that later. If you're talking about just how do we refine a model, then that's in the process of building the model, and we'll talk about that also later. But it's really how you define the grid and then how it samples the property that you're looking at, like whether it's so you might have a nice contour map of porosity. You overlay the grid, and then the software will then say, okay, in this grid block, what's the typical porosity in there? And there's different ways to assign that porosity for that one grid block. But most of the simulators, or most of the, this would be like in Petrel, but most of them will look at an area around that one grid block and then do some averaging and then assign a value to that grid block. But so this is probably 100 feet, maybe like 60 feet. So this would be a relatively small grid block. If this room were a grid block, height wise, it would be relatively tall grid block. We usually, 10, 12 feet would be, well, it depends on the model, but full field models, you might have a 200 by 200 foot grid block, which would be fairly small, fairly refined, depending on how big the field is. If it's a medium-sized field, well, you might be able to get by with 100 by 100 or 50 by 50. But there's ways, and the reason why I'm telling you this is the finer the model, the finer the grid blocks, or the more refined the model, the longer it's going to take to run. And that's the key thing you're fighting against. You want to run it in a reasonable amount of time.
How do you optimize it?
So there are ways, and when we talk about gridding, I don't think we're going to talk about gridding today, but when we talk about gridding, there's ways that you can grid it such that you have more, and I'll show you examples where you have more of a refined grid in the areas that you really want to know more about. Then if you really wanted to do it, there's things called local grid refinement, which you can take cells and amalgamate them or combine them into kind of an area and then have small grid blocks within that. So it helps, but it will, and I'll show you in a minute, it hurts it hurts the solving. In other words, it takes more time to run simulated with local root refinement in it. And I'll show you why.
What's the reason of having this kind of price going up? Is there a specific reason, like, is it because there's more compatibility for it?
Which,
You said the grid block is really thin slice like a pizza box. So what's the reason behind that people think like or not even?
oh, well, because normally the area of the field is normally a field is pretty wide, and it's the aspect ratio of the field is pretty small. You know, there's some fields in the Middle East where they have long horizontal wells. And I'm trying to remember where it was, but I've seen them. And they're long. When I say long horizontal wells, we're talking about 30,000, 40,000 feet of a horizontal well. Yeah. We're not, because it was Oxidized, I think. Abu Dhabi, yeah. Yeah. So, but those fields are like as I'm told by the geologists, it's like a piece of paper, the aspect ratio. It's so wide, so big, but very, very thin. And that's why it's conducive for very long horizontal wells. So your model basically is, in order for have the resolution aerially and the resolution vertically, they tend to be, they're fairly thin, but large aerially. Oops. So because I'll be talking about this room as a grid block. So we're sitting in the grid block, right? And like I said, this is probably a medium size, and I admit it has a lot to do with the computing power that you have. If you have a 16 node cluster, this is probably a huge grid block. You might be able to run a full field model with 50 by 50 or 20 by 20 or something like that. But there's a lot of things going on elsewhere in the model that there's not a lot of activity going on, and so kind of a waste of time, especially like in the aquifer or in the aquifer. And I'll show you some examples of that. So bottom line is, if we're sitting in a big field reservoir, and then we're going to chop this reservoir up into all these little grid blocks, and that's where the magic happens with the equations that I'm going to show you in a few minutes. So we discretize the volume, and then the other thing we do is we discretize the time. So when I say discretize the time, we have distinct time steps are taken, and we'll get into time steps because there's time steps, and then there's time steps that you tell it when to take a time step, and then there's time steps that occur in between there that the model will determine what those time steps are. So we'll visit on that. So as I mentioned, if this was a grid block, all the properties within here are the same. I'll get in that in a minute. Now, the rates from time step to time step do not change. It's because your calculations your equation that I'm going to show you are based on inflow and outflow, and so the rate during the time step is a constant rate. But as we discretize, we do monthly time steps. Well, you'll allow that rate to vary by month, and it looks like a nice decline curve. But for the sake of our equations, we have one rate in the time step. Yeah.
Hello, Professor. I understand based on your explanation, I understand the discretization of volume, but the time aspect is not yet clear to me. How do you discretize time?
Say that again.
You explained that discretization has two parts, volume and time. Okay.
Yep.
Volume discretization is clear to me, whilst time discretization is unclear at this time.
Okay, so basically what we're saying is, if we're going to want to model, let's say 10 years of history, we divide that 10 years of history into, let's say, once every year. So if we have a time step every year, then we're discretizing that 10-year period into 10 different time steps or time intervals. Okay, so we normally, obviously, in a 10-year model or 10 years of modeling, we probably would chop it up into at least quarterly, probably monthly, but we could do it daily if we want to. So it depends. If we're doing a well test, for example, you might have it every few seconds. So it really depends. But all we're saying is we're chopping up time into intervals. Okay, just like we're chopping up the area into, or the volume into little blocks, we're chopping time into intervals. Does that make sense?
Yeah, it makes sense. So what we are saying in essence is that you have control over that in the model. You can specify it in the model, right?
Yeah, and I'll get into that because there's a bit that you need to know about in terms of specifying the time steps. So
Okay.
there's some
Right.
obvious times that you're going to want to specify, but then there's other times that the model will do it.
All right. Thank you.
All right, Jessica.
Professor, when we are locating each well in the grid, we must use target coordinates or surface coordinates.
Okay, so yes, use both, but we'll get into that too because the location of the wells, there's some assumptions that we make about the locations of the wells also. Okay, so I'll get to that. The dynamic properties like the pressure and let's say rates or saturations, or not rates, but saturations, those are calculated only at the time step, the end of the time step or the end of the interval. So if we have, and this gets back to the same thing, if we're talking about a volume of reservoir that we're chopping up into blocks, the more blocks we have, the better resolution we have, and the better the solution. If we same thing with time, if we chop it up into 10 years into 10, that's a lot of things that are going on in that 1 year period. So that's why we want to sometimes chop it up into very, very small time steps to see what's going on. Particularly, let's say if we're studying, let's say coning or something, then maybe something near wellbore effect that doesn't last for a long time. So, but just keep in mind when I show you these equations, those equations are occurring. We started at a particular point in time, and then we end at a particular point in time, and we really don't care what happens in between them. Kind of like a material balance, right? In material balance, you have you take a point in time, and you figure out what's going on, and what's ever happening in between. It doesn't matter. It's what the reservoir looks like now and what it looked like, when you started that. So, getting more into the discretization, and I have more slides to show this process, but every grid block has a single value of at least a single value or at least few values of, and I'll explain why I say that. So in our grid block here, we're sitting in this room, and our porosity and our net to gross value, those things are multiplied to get the net pore volume, but that is there's only one number for that inside this grid block. Okay, and so you can imagine, and same thing with transmissibility and net to gross. Transmissibility is a little bit different character because it's really between blocks, but we'll get in that. The oil, water, and gas saturations, the oil, water, and gas pressure. And as you know, we could have different pressures for oil, water, gas because of caliper pressure, right? And then oil, water, and gas relative permeability. Now, here's where I would say a little asterisk on this, because relative permeability, it would make sense that we have one value of permeability or reservoir or relative permeability. But in our model, we could actually have directional permeability. So, and we could do funny things where we might be able to have flow in one direction easier than flow in another direction. Now, it's easy to think about directional permeability because sometimes there's anisotropy and you have flow in this direction different than this direction, and that's why we have permeability value for X, Y, and Z. Almost always we have a different value of permeability in the Z direction than the horizontal direction, but sometimes we have it in the aerial direction different. X and Y. So the point is that permeability, there could be at least 3, and there could be more. But for the most part, we use 3. Or maybe 2, right? X and Y is usually equal, and then Z is going to be different. And we'll get into how you define that in the model. Okay. So let's look at this. Yeah.
So what about the ability to go to
raw property. Like, if there's clay content and stuff.
Yeah, so really, you're talking about facies there, facies, and usually that results that you do that, you know, in the before you get to the dynamic phase. Talked about that last week, right? But usually all that stuff results in a value of porosity for a particular grid block, right? Because you'd have the different facies and then you apply it, and so but you still end up with one value of porosity, maybe one value of net to gross, and then one value of permeability, or two values that X, Y, same, Z different. But that's all that stuff that when you're talking about facies and all that stuff, that's all done by your geology group. And then now your model still has one value of each of these. It looks pretty, it's nice and distributed and nice, but your model still only has one value of porosity. And that's one of the reasons why, if they spend a long time and doing all these facies modeling and all this with the seismic, then you probably want to have a fairly refined model to capture all those heterogeneities that they had, both aerially and vertically. Okay.
So the alignment on this, the type of model, the size, comes again from the static model that the geologists do with them.
Well, we'll get into this, but it's more of a function of how much time what's the duration of the history and how many wells, let's say, and how much time you want that model to run. So it all boils down to you being able to run that model in a reasonable time frame. So all those factors come into play. So let's suppose now this is a little anticline, or with a faulting, just an odd little shape. But anyway, so we have gas and oil and water. So gas, it's a gas reservoir. Now, some folks in some parts of the world, so as you know, oh no problem, come on. Hello. So we're recording, so you'll have to catch up later. So the standard nomenclature in terms of colors for saturations, blue is water, right? And in the US and many parts of the world, red means gas, and blue or green means oil. But in some places around the world, that's flipped. The oil and the gas are flipped. So here we're talking about a gas reservoir, but and so you can look at this as and a lot of times when we're looking at models, we look at it in a highly exaggerated way. So most of the times you'll have a 10 times exaggeration so you can see the structure and whatnot. So one of the things is when you're making displays, you want to make sure you have a little symbol or something like this to show the exaggerated scale. Now this, it could be exaggerated, it's just it could be or it could not be, it's just a simple little discretization. So this is our reservoir. We have oil or gas over water, and then we sit there and say, okay, we're going to discretize that structure. And so I'm overlaying these grid blocks, so to speak, that we're going to chop this reservoir up into these different grid blocks. And so this reservoir would now look something like this, where you have these are all gas cells here, and they're 100% gas, or actually 101 minus the conate water saturation, right? But this would be the fully saturated gas. And then you have a transition zone here. So some grid blocks are in the transition zone, some are not. And then you have these, which are pretty much water or a combination of a little bit conate, instead of 100% water, it's going to be 100 minus a little bit of gas, right? Because it's just so happens where we have that grid block. So we go from this, which is the real reservoir, to this, which is our representation in our model. Okay. And then we'll talk about gridding later on, but just for your information, and you'll see it in a minute, we have 1, 2, 3, 4, 5, 6, 7 cells. And usually, it's not always the case, but it's generally the case. when you have a reservoir, it's not a square, it's going to be elongated, it's going to be a rectangle or something like that. So usually the direction that is the longest direction is usually the X direction. And then the other in the aerial direction is the Y direction. And then of course, in the vertical direction, it's always the Z direction. And then I'm going to use the terminology for X, Y, and Z. In that, usually we use X, Y, and Z to determine the direction or discuss the direction from a mapping perspective. After we go from a mapping for real world into our grid, our nomenclature switches from XYZ to IJK. And the reason why we go IJK is because now we're defining a grid block, IJK, as opposed to an XYZ or a, in whatever coordinate system you have. So this would be a 7, and then notice it's 3 in this direction, and then it's 3 in this direction. So this we'd call this a 3D model, and it would be a 7 times or by 3 by 3. So that's how we would define that model from a dimensional standpoint, 7 by 3 by 3. Okay, so you can see how this and these two look very similar. And you could also see that, okay, this is kind of coarse, right? But when you're looking at certain areas within a full field model, it's going to look like this. It's going to be fairly coarse. Okay, so now let's look at another little illustration. Now this is a 1D model, and the reason why it's 1D, one-dimensional, 1D, is because we have 1, 2, 3 cells in this direction, and then only one cell in the Y direction and only one cell in the Z direction. So this would be a 3, 1, 1 model. Okay. So let's say we're injecting water here. This is an injector. If you can't tell that, there's a little arrow there. So this is an injector. And I know this is a kind of crude way of putting it, and no pun intended, but here's our oil. And then we have gas. So it's just showing how we might represent 3 phases and in an injection scenario. So we discretize this. Let's say this is the real reservoir. We discretize this into 3 different grid blocks, which if you were to separate out or segregate the phases, it might look something like this. There's really no oil or gas here. Let's say it's been injecting for a while. And then here we have water, maybe something above connate water saturation. You have a little bit of oil saturation and a little bit of gas saturation. And then in this grid block, you have a little less water, maybe about the same oil and a little bit more gas because it hasn't swept there yet. Okay, but that's just for illustrating purposes. What really the model looks like is this. These 3 saturations, they're 3 different distinct saturations, representing each of the phases, but in the model, it's dispersed. Everything is just there, right? And we'll get to that in a little bit when we talk about numerical dispersion. And I'm not sure where we talk about that today or not, but we'll see. We will talk about it because your project A is all about numerical dispersion. So, yeah.
So it looks like they are vertically discretized. Why can we do it horizontally discretized?
You can. This is just an illustration, but yeah, we discretize it all directions. And there's reasons why you might have a perfectly homogeneous sand, and so you could represent that with one grid block, right? But let's say you put a horizontal well in there. Well, you're going to want to see the variation in pressure and drawdown, the drawdown and the pressure as it moves away from the well. So you might want to have that nice homogeneous reservoir to be subdivided into many different layers. So we could, let's say, look at different KV/KH ratios when we have a horizontal well right down the middle of it. Okay. Same thing with, let's say, a partially penetrating well where you have a well, let's say the well's top to bottom, but it's only perforated in the bottom quarter. Okay. So the and we'll get into that later, but we call those engineering layers. where you put those, you have different resolution, different layers, because you want to see something from an engineering perspective, as opposed to geological layers, because the geology dictates these layers. Okay. Okay, so let's talk a little bit about the mechanics of how we do our calculations. And it's, remember I mentioned the material balance, Darcy's law, and discretization. So this is the material balance part of it, where we have a grid block here. This is a single grid block. And we want to take into consideration, and remember I said X, Y, and Z, and so this is kind of elongated here, so that's X direction, but it is one grid block. So, so we want to look at what's going into the grid block. So that would be stuff, let's say, flowing in from that side, versus what's maybe going out. And I guess you're looking at it this way, the other way, but so we want to know what's coming in from that face, what's going out from that face. So we keep in track of that. And then we want to know what's going in, you know, coming in from there and what's going out there. And we want to figure out what's going out from the top to the bottom. And if we keep track of all those, just like material balance, if there's any difference, it's an accumulation, right? So we have flow in minus flow out equals accumulation. This allows the discretized volumes of rock or the grid cell to be treated like a material balance tank, like we all know. Okay, so and you've all done material balance calculations, right? You probably have defined or solved the material balance equation. So this is not material balance, but it's Darcy's law, right? That should look familiar to you. And if you know, in Q is flow, right? And then P is the phase, and area, and Darcy's law has an area term, right? Area times, normally we have one permeability term, but which is effective permeability, but we have our absolute permeability, which is K, and then KRP is the relative permeability for that phase, the same phase here. And mu P is the viscosity of the phase. And then delta P of the phase, so the change in pressure. Now, you know, I haven't talked about what that change of pressure is, or area, or for that matter yet, but I will. And then this rho P G sine theta is just to take into consideration a change in elevation of, let's say, two different grid blocks, because it's not all flat. So this equation allows us to allow this grid block to communicate with the next grid block, or is said in a different way, it allows us to calculate what the flow in or out might be. And whether it's in or out doesn't matter. It's just a change in the minus sign or plus sign. So this, you know, if we chop the reservoir up into, you know, small enough grid blocks, now we are able to model the flow in the reservoir.
So, Professor, so the angle, what's the angle? Is that a deep angle or
The what?
angle? The angles, the theta, the angle, the reservoir angle, is it angle to the horizontal, or is it the deep angle? From that's the equation. The sine theta, the angle.
Oh, the angle. Say, yeah,
Yes.
it's the angle. It's the angle when you're looking at one grid block to the other grid block. So if this grid block goes up here, it's that angle. It's just the elevation. Sine theta is the height, right?
Okay.
If the values like of pressure or compressibility are associated with the square law.
Yes. So compressibility. Compressibility is a term we have, but it's not necessarily an individual grid block pressure. It's not an individual grid block value, but the compressibility will impact or affect the porosity of that grid block. So porosity is an individual grid block, and it will be impacted by the compressibility and the change in pressure.
We will know the compressibility. Okay, what about pressure?
Yeah, so each grid block, we have a value of pressure, which I'm going to show you in a minute. when we get to the equations. So let's look at this whole picture. I'm leading up to the equations. So we look at this whole picture. Here's our little reservoir here, and we're injecting water here, and it's kind of a meandering stream. And then we discretize that. I showed you that, and then this, we're just separating out the different saturations just so you see them. So we discretize that, then the material balance or the volumes that are in here of the different phases. But then going from one grid block to the next grid block, we apply Darcy's law to talk about what's communicating. And so we have material balance, Darcy's law, and then we have our representation of our reservoir this way. But again, everything's dispersed, right? Now I will say there are some models that have a mode that you could run it in. It's called vertical segregation mode. And it actually it keeps track of the height of these things. So it gets a little complicated, but if you for some reason want to do maybe a sophisticated material balance, and you had perforations that you were trying to see what would happen in terms of, let's say, encroachment of water, they do have this vertical segregation mode, which actually looks more like this, but very rarely if that's ever used. So don't worry about that. But I had to be true to my slides. So so let's I'm not sure why we put this slide in here. I think we wanted to revisit this, but we'll talk about fluid treatment later on. That's because this slide comes from our PVT section, and we'll talk about. But I just want to point out that for black oil models, oil, gas, water are the components, but they're also the phases. So we treat them. That's how in the equation that I'm going to show you are all a black oil. Okay, actually it's one phase in a black oil. So the rules for how the phases interact are based on input tables. The compositional treatment, there are multi-components in there, oil, gas, and water phases. So we have both the phases and the components, or the composition of the fluid. And then the rules for how the phases interact are based on an equation. It's an equation of state, and we'll get into that later. But just wanted to show that everything I'm going to show you next in terms of the equations and whatnot are black oil. Okay, so let's kind of briefly go over what I'm going to talk about in a minute. So Y is the vector of unknown values, the pressures and saturations being solved for at the end of each time step. And so I'll show you, because we're going to set these up as residual functions such that we solve for the errors. So the pressures and saturations, normally, and these we'll talk about three-phase, but normally it's a three-phase model: oil, water, gas, and then we have pressure. When we're doing our solving, we normally solve for 2 saturations and 1 pressure. There's 3 equations and 3 unknowns, but we know that the phases have to add up to 1. So if we solve for oil and water, then we can calculate the gas. And that's normally what's done is we solve for 2 of the phases and then just set an equation up equal to 100%. Fy is the vector residual function. The errors Fy values approach all
Sorry,
zeros.
Professor?
Yep.
So you said, your previous statement, you said you solve for 2 saturations and 1 pressure.
Correct.
So is that assuming the pressure is same thing, is uniform?
So, well, yes, we're assuming the pressure is uniform and the saturations are uniform within each grid block. We're still talking about within a grid block. Okay.
Okay. Okay.
Yeah.
Okay.
Okay.
The rate is also constant.
What was that?
The rate is also constant. The rate
The rate?
is also constant.
Yeah, yeah. So, and we'll get to that when we set up the equations. Yes. T is the transmissibility of each phase calculated between the cell and each of its neighbors, which depends in part on the cross-sectional area. Let's suppose that these grid blocks are all, there's no faulting. Okay, so that means that face is perfectly aligned with the face next next to us. So that becomes the area that we have in our equation. If there's some shift, then the area changes a little bit based on what's juxtaposed, okay, or common or juxtaposed. M is the mobility of each phase, and I'll show you the equations for mobility. And then delta y is the vector of correction. It's applied from one vector y to get to the next vector, and as you get closer. And then J is the Jacobian matrix, the matrix of first order partial derivatives of the residual functions Fy with respect to y. So we're going to create a Jacobian. We're going to solve for that. And then we use that and come up with the actual values of pressure. Then we're going to see if we're in tolerance. And then we're going to, if we're in, we move on. If not, we resolve. Okay. So this is what this thing looks like in terms of equations. So here we have T or tau. It's some use T, sometimes use tau. Tau O. So this is the transmissibility of the oil phase at I. It's hard to read, but that should be I plus 1/2. And then the delta P of the oil, so change in pressure of the oil. And notice it's T or I plus 1 and I. So the delta P is the change in pressure from two different time steps. The transmissibility is the transmissibility halfway between the cell centers. I guess I should say that. All our calculations are assumed at the cell center. So and the reason why that's important is everything occurs at the cell center. And so if we have a let's say a square cell here and an elongated cell there, the transmissibility is going to be whatever is between the two cells. And so it's just whatever is the transmissibility of that cell face. And so if there's if you're using permeability, you have to use the permeability that's effective in that distance from the cell face to that. And then same thing with the transmissibility as you go from in that cell face to the cell center on that side. So it's just yeah.
If both the sets are not same, then it won't be at the border of the
Yeah, well, no, if both are the same, then it's exactly right halfway between them. And that's why it says I plus 1/2. So, but if it gets a little bit complicated, but you don't have to worry about any of that. The simulator calculates the transmissibility for you.
Yes, so just to compare what just said, transmissibility is the value between two cells, right?
Correct.
Center to center.
Correct.
And the pressure that you've indicated is what?
So the pressure, so this pressure is the cell block pressure from one time step to the next time step. So this is I plus 1 and I. Okay, so remember there's one value of pressure, and that is a value that's assigned to the grid block. All right.
Okay.
Okay. And then, so now we're saying, okay, what's the transmissibility and then delta P? Basically, Darcy's law, it's kind of, we're talking about what's the transmissibility there, what's the delta P? And so we're really calculating the flow going from this one to this one when you have a delta pressure. If you have strong delta pressure, there's a lot of flow. But it also depends on that the transmissibility. And then, so I guess we can go here. So if you look at this, this is the transmissibility equation. So it's our part of the Darcy's law that has our area, our permeability, and then M is our mobility term, and then X minus X1. So we're looking at the distance between those, because remember, Darcy's law has a distance component in there, right? So there's a length component. That's what that is. So M is the mobility. Now we separate the mobility of the O at that time step because at the top we have KRO. That's the relative permeability of the oil at that time, and then V sub O and mu sub O at the at that at that time step or that point in time. And why is it so? Relative permeability, B sub O and mu sub O, those all vary with pressure, right? So depending on what the pressure is for the grid block, we're going to have a value for a different value or a value for the permeability, the B sub O, and the viscosity. Okay, so this is completing our Darcy's law equation because we need to know what that value is at that time step at that pressure.
Could you say what I plus half would be like?
So I plus half is the I plus half. See, that should be. Yeah, I think this should be. I think this should be T plus 1 and T. But the I plus I half and I minus, so that's in the I direction, halfway. So basically we have these values for this grid block from, and remember, okay, Darcy's law, we're using Darcy's law. The assumption is everything is between the two cell centers. But so we have a value of mobility for this grid block, half of it, and then we have a value for mobility for that grid block, this half of it, because we're looking at the difference between this cell center and that cell center. So we're basically looking at this value of mobility. It's a weighted average between this grid block and that grid block. So if this grid block was really small and that one was really big, and you'd have a very small component, it'd be a small weight to this grid block versus that grid block on the mobility.
I believe the direction of the time step.
I is the direction. It's the I. This should be. I believe that should be a T. And then we have here, and you could check these in Maddox and Dalton. Okay. So this is the delta P and the transmissibility. Transmissibility has the mobility component, and then this is I can't read that, but this is the transmissibility I minus 1/2, I plus 1/2. That's plus 1/2. Okay, so it's in between. It's the transmissibility in between the grid blocks. But since Darcy's law incorporates not only the area and the permeability, it also includes the delta P, and that delta P is from one time step to the next time step. And then we have over here our volume. So this is our accumulation term, porosity, and our oil saturation, and then V sub O minus our porosity, oil saturation, V sub O, and N plus 1. And so the N plus 1 and N, see, I believe that's the time step. That's the accumulation term. So this minus this is a different time step. So so I'd have to check this, or you could check this. This I plus 1 and I minus 1, I think they messed up the nomenclature to be, this probably is N minus 1 and N plus 1.
Here's what's been taken, N plus 1 is to be considered.
Oh, yeah, because we separated these out. Yeah, but that should be two different time steps. Yes.
Yeah, yes.
Yeah. So I think this is this is okay, but I think this is, and it might be because different books and different they use different things for N being time step, T being time step. But the main thing is that you see that this is the equation set up, and then we set this equal to 0. Now that we set it equal to 0, then we could solve for it using our matrix. So if we look at the vector equation,
Professor, so
yep.
the assumption for setting the entire equation to 0 is that no accumulation within the system, right?
Say that again.
The reason for setting the entire equation to 0 is because we are assuming accumulation. There's no accumulation.
No, there still will be accumulation, but we set it to 0 because if it all equals 0, then we're done. We solve the equation, but we're really solving for error. And that's why we're solving for 0. Yeah. And so this, if you look at this, this is the F equals the same equation we have, it's just all equal to 0. So now we have a matrix that we set up that's F of Y, and we have all these for the different phases and for the different grid blocks, and equals Y. And then this is where we solve for, or we solve this. And once we get to 0 error, then we're done, but we never get to 0. We get to a small tolerance and we accept a bit of error. And then once we get to that small error, then we calculate the oil saturation, water saturation, water saturation of all the different grid blocks. Okay, now this is being done simultaneously for all the grid blocks at the same time, all the grid blocks. So once we have our equation set up, F, Y, F, and then we could solve for, we solve for the components of oil and 2 saturations. So we want to find the pressure and saturation values such that when we do our solving, we get to a close to 0. Okay. Now, unfortunately, Y is nonlinear, and the following approach takes us to the right values of Y. So then we set up this in a what we call a Jacobian, which is our matrix, and we use various matrix solving, which it's been a long time since I've solved a matrix. You guys have probably solved one more recently. Maybe you not so much. But the point is, guess what? We don't have to worry about that. And when I was working for Chevron at the time, Chevron developed their own simulators, and they would spend a lot of money and time and effort, and they would pay someone like J.S. Nolan. You'll see in some of these things, you'll see J.S. Nolan's cover to do the matrix work, because that's one place that you could speed up your model run times and get a competitive advantage. Okay, but the good news is you don't have to worry about any of this. I mean, sometimes we had to worry about things like, well, if this was this, and you'd have to, your head would explode, because only the mathematicians at the lab would know the best way to do it. Now the simulators, they spend a lot of money on this, and they spend a lot of money on optimizing it. And I'm going to show you in a minute. There's some good news about how these matrices are set up. That it helps. You can define some matrix solving techniques that capitalize on these. They're called banded matrices that capitalize on that, so they could actually solve them a little bit faster and better. Okay, so we have this Jacobian that we have to solve. So before I get into some of those the interrelationships, which is important, I needed to kind of jump back and talk about black oil and composition models, because it's important. So in black oil models, we have three equations and 3 unknowns per grid block, right? And you saw the equations, and we're solving for the 2 saturations and 1 pressure. We back out of the 3rd saturation. So compositional models, though, now we have 2 times the number of components. So, when I say components, methane, ethane, propane, and nowadays you used to get a lab experiment, and you probably have seen them in well files and whatnot, and it might have to C7 plus, and then you have a plus component, and they combine everything into that plus component. Well, now you regularly see C30 but you have to we call it lumping. You have to lump those components together to bring it down, even though you have it refined down to 30 components plus a C30 plus or a C31 plus, whatever it might be. You can't run a model with that many components. So we start grouping them. So methane will be one, ethane will be another one, and then maybe propane, or maybe propane plus others, the light ends, and then you might divide them up such that you have a reasonable number of components. And the reason why I say that is 2NC, which is 2 times the number of components plus 2 equations per grid block. Well, if our black oil model runs in, let's say, 3 hours, if we would have a compositional model, and you're not going to have a compositional model with, let's say, less than 7 or 8 components. So let's say 8 components now, it's 16 plus 2, it's 18 components versus, so you have 18 equations versus 3. And then remember, since we're solving in matrices, it really changes, it affects the time when you go from, let's say, a typical black hole model and a typical compositional model. And then thermal, we add a couple equations for the heat.
So for the black oil, each component acts on the same window,
So
that oil, gas, water, and other things.
yeah. So remember, we had the equation, and then it was that was only just for the oil phase, and then you have water. Okay, so let's talk a little bit specifics about modeling now. So we have these different formulations, and this is important. So we have what we call a 5-point formulation and a 9-point formulation. The equations typically would apply to a 5-point formulation that I just mentioned, because what we're assuming is that there's no, or let's say, I shouldn't say there's no, there is a minimal amount of flow in the diagonal direction. So, and don't worry about the numbering of these cells, but 1, 2, 3, 4, 5, 6, 7, 8, 9. And so let's say it's an aerial grid. Now this would be a what by what model. Three by 3 by 1, right? And it's a 2D model, right? Because we don't have any resolution in the Z direction. So it's a 2D model. And what we're showing here is that you have 5, which grid block 5 directly communicates with 4 and 6 and 2 and 8. Okay. Now, for reasons that I can't explain, but someone else with better mathematical acumen could, if you start looking at the flow, looking at the equations and the solving and the solvers, if you look at if you set up a model and these are perfectly orthogonal grid blocks, in other words, they're perfectly rectangular or square, but they're perfectly rectangular. In other words, all these are 90 degrees. Then the error that and you could set up the equation such that you have flow from this one to this one and this one to this one. It gets a little complicated because guess what? There's what is it's easy to figure out what the area is between this one and this one. But if you want to set up an equation between this one and this one, what is the area there? Like I said, there's people a lot smarter than me that could answer that question better than I can. But in respect to what we're doing, if you have perfectly orthogonal grid blocks, you can ignore the flow going from 5 to 1. And the reason for that is it's like several orders of magnitude lower if you take that into consideration. So it's no big deal. Now, if that aspect ratio was quite different, and it was, I'm going to draw something. Oh, I could draw. Well, no, I can't. Well, no, that's okay. So if these were squashed, let's say, and these were let's say the face here is very small and these are closer together. Maybe there's a lot more flow going from this one to this one. Yeah, I don't think. Huh? Yeah, I don't think that's working. I don't think they're going to be able to see it. So if you had a group like this, that's what I was trying to say. So maybe it would be, but that's okay. So the point is, so if it's orthogonal, I'll show you some examples of non-orthogonality. So I have some slides that will explain that. But if it's purely orthogonal, then the error that you impose in your model will be very minimal. And so you don't have to worry about it. Okay. And I'm going to show you ways that you could check it. In this one, this model, it's what we call a 9-point formulation, because we actually have equations that do the calculations for, 5 to 4 and 1 and 2 and 3. So that middle grid block for all of them. So we could set that up too. It just, guess what? It's going to take more time. I'll show you why in a minute. Okay. Now, let me show you something else. So this, I'm gonna show you the matrices and Jacobian for a model like this. Now, this is, again, this is our 2D model. It's a 3x3x1. And then we have a well here, and notice that it's a horizontal well. So it's completed in cells 4 and 5. Okay, so what does that look like in terms of our matrices? So each X here is representing pressure. You can't see it, but pressure, saturation 1 and saturation 2. And that's each one of these are the phases. So that's 3 equations. Each of these are an equation, but for each of the phases. Okay. But each of these coefficients are here. So, and then where's our well? See, our well, we have our well is here and here. Cells 4 and 5 is our well. And then on the solving part of it, we have our wells here. So, and this is adapted from Nolan, by the way. Nolan was very popular in the 90s or even before that, because his company spent a lot of time selling these solvers or these optimized solvers to companies like Chevron and others. But notice that this is it's what we call a banded matrix. So these, and it's banded because we're showing, where we're communicating between cell 1 and cell 4. So what I mean by that is cell 1 and 4 talk to each other. Cell 5 talks to, let's see who. Cell 5 talks to 2, 4. That's cell 5, cell 6, and cell 8. Okay. So this is showing this type of configuration, right? 5 talks to 2, 4, 6, and 8. Okay. So notice we have nothing in here to bother us in terms of solving this matrix. So these solvers, they spend a lot of time and effort because there's nothing in this matrix here and here, and so you can capitalize that and spend all your time optimizing for this type of a matrix. All right. Now, so this is this 5-point formulation, right? And with the horizontal well. Okay. Now, let's suppose that we impose a fault here. And I'm just going to do a very simple strike slip fault because it's a 2D model. And what I want to show you is how does that impact the Jacobian. So now, all of a sudden, 5 now does talk to 9. Before we ignored that, right? Because it was a diagonal. But now 5 talks to 9 here. And 5 still talks to 8, which it did before. And let's see, 5 talks to 4. Still had that before. And 8 talks to 4. So now 8 talks to 4. Before 8 and 4 were not talking to each other, right? So just by having this little shift, we now add some elements to our matrix that we didn't have before. And the only reason why I'm showing you this is because in real life, we have faults.
This will be a strike slip. Strike slip equation.
Yeah, this is strike slip, but most times it's what we model is a displacement fault, vertical displacement. But the important thing is that when you start to introduce these real life things into your model, we have more elements, and those additional elements take more time to solve and run. That's the only thing I'm showing you this for, is that on why all of a sudden, if you add a default to a model, your model is taking longer to run. Why is that the case? Well, because you've made it more complicated from a solving perspective. Let's do this. Let's so remember we had our 5-point, yeah, and then now we added a default. Let's go back to get rid of the fault, but now we've done we've added to have our 9-point formulation. So now we're looking at 5, talking to 1, 3, 9, and 7 that we didn't talk to before. Okay, so now all of a sudden we're, you know, and the more we fill this banded matrix up, the more time it's going to take to solve in order to get the residual to close to 0 in order to move on to the next, right? To get our final numbers and then move on to the next time step.
I'm kind of lost here, but I think I'll catch up later.
So each X represents a number which is related to the derivatives of mobility and volume with respect to changes in pressure and saturation. But the main thing, what I'm trying to show you is the difference between this. Notice this is a 5-point formulation. And notice there's nothing here and nothing here. And now this is a 9-point formulation. And we've added these yellow ones, this one, this one, this one, this one, each of these, we've added those. See that? Okay, so the whole point to this is that we can have better resolution, and we could always run it in 9-point if we want. And by the way, when we go to 3D, the 5-point becomes 7-point. And the 9-point becomes 11-point. So when we have a 9-point, we only worry about the one right above and right below. You could have a 27-point, but yeah, I've never seen that in a commercial simulator, and I've never seen it actually. I've just heard that some research is done on a 27-point formulation. Yeah, so when we go to 3D, we add above and below. So that's why you just add 2. You go 5 to 7, 9 to 11.
Okay, but for example, if you don't use the 9-point, you're using the 5-point. But when the number 4 communicates with the number 1, we'll still maintain the same quantity balance.
Yeah. So the equations are still the same. It's just which ones are communicating with each other. So when we set up the equations, set up the matrices, it just depends on which formulation we have. The equations are all the same, and the solving of them simultaneously is the same.
So we're going to still have the same result if we use the 9-point.
Yeah. It'll look the same. It's just there might be some errors imposed, and I'm going to show you how you could check for that. So this is a little complicated, but I just wanted to show you it's the inner and outer loop. So we begin at time 1 or time -1. I guess that's what it is. But we know the values of all the pressures and saturations, and then we want to advance to the next time step, T plus delta T. I guess that's a T.
So at first, you're getting, right?
Huh? So when we initialize the model, we're in equilibrium, but this could be any time throughout the model run. So this is like, let's say December 2010 to January 2011. Okay. So then we say, we started that time. We know what everything, we solved that, whether it's initialization of the model or we just solved it from the previous time step, we know what the numbers are. Then we're going to guess values of pressures and saturations at T plus delta T. So there's algorithms on how we guess this. A lot of times they might use the same numbers and advance the time. And then we calculate the error or the residuals, right? The F equals 0, whatever that's 0, it's not going to be 0. We calculate what that is based on the assumed values, whatever those might be. And then we ask the question, are the residuals small enough? And then if they are, then we know what the values of the pressures and saturations are. We accept the values of pressure and saturation as correct, and we advance to the next time step, T plus delta T, or T plus delta T. If they're not small enough, then we calculate the Jacobian, and then use a matrix solver to invert the Jacobian. And this is usually an iterative process. We invert it, and then we use the inverted matrix to calculate the changes in the assumed pressures and saturations, apply these changes to the values, and arrive at a new estimate of pressures and saturation at time t plus delta t. So we have this inner loop that's solving and inverting and setting up the Jacobian, solving it. And then we have this, then we calculate what the pressures and saturations are. And then we go to this next question and said, is the error small enough? What we calculate the error of the residuals, and then we ask, are they small enough? And we move on.
That will keep feeding on itself until you get it smaller.
Correct. And sometimes you might never solve. And so sometimes you'll get some messages that you have an inner loop error, and some simulators call it something different. Or they'll say, it wasn't able to converge. And so there's some things, and we'll talk about what to do with the model to help make it converge. You had a question?
When you calculate the Jacobian matrix, what do you have to calculate this?
Yeah, it's actually inverting the matrix and solving the matrix with that guess value. And this is where the matrix inversion and matrix solving comes into play. But you don't have to worry about it. It's all done by the simulator. The only thing I'm showing you why we're doing this is really to show what happens when you start to mess with the grid, particularly when you add what we call non-neighbor connections through a fault, or how sometimes relaxing tolerances could help converge the model and get you to solve the model. Some very complicated models will have they'll chug, they'll have time step chops, and we'll talk about that in a little bit, but they'll have a tough time solving, and then you might need to do some things to make them solve faster or easier. And what I'll say it right now, because I'll say it again later, but one of the easiest things you could do to get your model, whichever formulation, which we'll talk about in a minute, is to reduce your time step size. It's kind of like taking a bite of an apple. If you take too big of a bite, you can't bite it, right? But if you take small bites, it's no problem. So it's the same thing with simulator. You take little time steps, because there's not that much change between when you start to reduce the time steps. If you try to go too far, then the difference between what the pressures and saturations are here and here are too different. And so it's hard for the model to converge.
For this phase, 2D phase and this phase.
It's for all. We set up the equations. It's these equations.
There's a block. Phase block.
Darcy's law? Yeah, so that's built into these equations. Remember, we set these equations up back here back here. This has Darcy's law and material balance. These are the equations that formulate the error function that end up with in the Jacobian. These are the equations, each equation in each grid block, 3 equations for each grid block for the 3 phases. So, yeah, and so we're solving for pressure, saturation.
For each phase.
Yeah, all 3. This is a 3-phase. This is a 2D model, 3-phase with 1 well connected. The 1 well is completed in 2 different grid blocks. No, 3 equations. 3. Each of these are coefficients in the equation. We're solving for pressure, saturation, and saturation. So there's 3 equations and like 3.
After completing the Darcy's law, then we will go in this Jacobian.
Yeah, well, these are the same equations. It's the Jacobian is the matrix, and it's the process of inverting the matrix to solve for the residuals. And if they're small enough, the matrix inversion is another iteration in itself. And once that's done, that's where you get into matrix solving, because it's an iterative process. They're non-linear, so you have to iterate on the Jacobian. And then once you get the Jacobian, then you go to solve for the saturation. And then if the error is small enough, you move on. Okay, so we went through that.
Sorry, Professor, just I know, like I said earlier, I'm kind of lost, but I will catch up later on. I'll watch the video to understand better. But my
Okay,
question is, what are well residuals and what are the unknowns?
I'm sorry.
The unknowns-
The audio is kind of tough here. What was that again?
Okay, the unknowns are the pressure and the saturations, right?
Correct.
So what are the well residuals?
What
What do you
was
mean by well residual from the previous slide?
This here?
No, go to the previous one before this.
Yeah, on the top, the very residual.
Yeah, here. Well residual.
Oh, okay. So
Residual.
basically, we have we're solving for zeros, right? And this is just saying the wells, there's a couple elements here for the wells, because you need to solve at the same time the same items for the well block. Because the well block is special because it's got source and sink to it. Yeah. Okay, see if this slide helps. Maybe it doesn't. So we at time t, we start with our error function at 0. We're assuming them 0. We calculate our Jacobian, and then we solve for the Jacobian, and then we solve for so we're going through this phase here where we're inverting the matrix in order to get our residual functions to be small enough. And then we do that, and we see what the saturations and pressures are, and compare that to, and look for the error in the saturations and pressures. And then we continue to do that until the point in time where our calculated, when we solve our Jacobian at t plus delta t, the errors that we see, are they small enough to accept the values of pressures and saturations at that outer loop? And if they're small enough, then we move on. And then we start again with this next time here with the values of the YR. Okay, so, and well, so we usually have so default values that are acceptable, and it depends on the model, but you might have like a PSI or a fraction of a PSI, that in terms of error. And then same thing with the barrels, and it's going to be a small number. But in some cases you don't solve, and if you can't solve, you might actually relax your tolerances. And so you relax your tolerances so you are able to solve it. And some of the reasons are that there might be a lot of things that are going on in your model that, and sometimes it's a hiccup where you put a new well in, all of a sudden it's having a tough time solving. So you might have to, and most of the simulators today will have algorithms that do this for you, that you don't have to worry about it, because you put a new well in there and it might just automatically take smaller time steps. And then, well, we'll get into time step here real soon. In fact, let me talk about time steps in a minute, because there's time steps that you impose, and there's time steps that the simulator will impose. So, the whole purpose of this is not to figure out matrix inversion. It's just, again, to show why your model is going to all of a sudden start. But more grid cells, larger matrix, more time, more phases. This was 3-phase. So if we did, you might have a gas field with only water and gas. You don't need to run, and you tell the simulator how many phases there are. So if you have a gas field with no condensate or no oil, just use a 2-phase model, and it'll speed up. More wells, larger matrix. So the more wells, you can see it does add to it, but not not tremendous, not as much as, let's say, non-neighbor connections would. So we could talk back again, and we talked about this already, but these slides illustrated Jacobian were based on a 5-point formulation, which does not account for flow between diagonal and neighboring grid blocks. Formulations is for the, okay. These models are more accurate, but the Jacobian features more terms, and of course that relates to more time. You know, remember, it's still the same size model, but there's more elements in there, and that takes more time to invert the matrix and solve it. Similarly, standard 3D simulation is 7-point, but diagonal elements are, like I said, it's 27-point, but I've never seen it. I know they've done research on it, but
Up to us to how we want to base those gridlock, like and why you did use that, like directly in front of each other, or do you want to?
no. So that will be a result of your geological group and how you grid the model. And we're going to talk a whole class about gridding. So don't worry about that. Okay. You will have non-orthogonal grid blocks in your model. You will. But here's the thing. You can run most models, CMG, you could run it in 9-point or 5-point. So if you were concerned, if you had a grid that all of a sudden you saw that grid had some very awkward looking grid blocks, in other words, highly irregular and non-orthogonal, you run the model in 5-point formulation, or let's say 7-point 3D model. And then you could run it in 11-point. You can look at the difference in the results. If the results don't look any different, then you know that, okay, there might be some errors, but they're not significant. And so you could test that every once in a while if you want to. You could continue running it in 11-point formulation. It's just going to take more time. But if you have a situation where you have some highly irregular, and I'm going to show you some examples of some grids that are highly irregular. None for us? We have 4 minutes. So if you think it's a problem, and I'll show you some examples where it might be a problem, you could always test it. In most of the simulators like Eclipse and Nexus and CMG, they're going to have these 2 different formulations, so you could try it.
I'm thinking there'll be like some difference, like fast.
Yeah, no, it's not going to be a big difference, but yeah, well, it could be. But I'll show you some examples where we run models with some pretty non-orthogonal grid blocks, and we've lived with it and accepted it, and we've tested it. Yeah. But all this is really just to illustrate, you know, some of the impacts that things that you might do to your model. Like if you impose some highly non-orthogonal grid blocks, you might have to run it in 11-point formulation, and that might make it twice as fast to run. I don't know. It might make a lot more, take more time to run. So it might be better for you to go back and regrid it without that if you find that to be an issue. Okay, so these earlier slides, what I'll talk about is what we call fully implicit formulation. Both pressures and saturations at the next time step are solved for. There is, and I don't have the equation for you, but there is an impasse solution that offers a reduction in time by solving for the pressure and then backing out the saturation. That's why it's called implicit pressure, explicit saturation. The Jacobian is smaller. It's a faster solution, limited time step size. It's much faster for some problems. Now, it used to be that you would tell the simulator to run it in impasse, and you could still do that. But most of the simulators today they just are fully implicit. The solution's a little bit better. It's a little bit easier, and the solvers today make it easier. Now, there are some simulators that do adaptive formulations where it might run in impasse in some areas and fully implicit in other areas. Like if you're way out and there's an aquifer and not much is happening, you could run it in impasse, and then over there you can run the whole model in it, but you could tell the model if nothing's happening much, go ahead and do it in impasse, and then where the action's happening, do it in fully implicit. Okay. And some of them will allow that to dynamically change during the run. Okay. So, this might be a good time to take a break. All right, how about 10 minutes? All right, thanks. Okay, so let's talk about time steps. Now, time steps are still wherever the simulator does its calculations. All right, and so while we were talking about every time we were solving the Jacobian and solving, that's at the end of a time step. Now, we call them report steps, are it's what you tell the simulator to stop at, and not stop at, to do its calculation. So most of the time we set that to be coincident with, let's say, the resolution of our data. And so let's say you have monthly production data. Well, you could do monthly time steps. You could do, and you could do, let's say, quarterly time steps if you have monthly data, but you have to take that monthly data and convert it to quarterly data. And by the way, I think I haven't specifically used the builder in a while, but I believe builder allows you to import monthly and then it does the conversion for you automatically, which is pretty nice. But it's assigned by the engineer and it notifies the model when changes or in rates or changes in rates or completions occur when the simulation results are desired. In other words, you can't get a printout of the pressures and saturations unless it's at a time step. Okay. Not only does it have to be at a time step, it has to be at a time step that you're asking for the information to come out. Okay, because the amount of output would be so much if you ask for everything you can ask for at every time step, it would be tremendous, especially when we talk about 3D data. So typically it's a day, a month, quarter, year in length, something like that. Occasionally some arbitrary period. There might be sometimes, let's say if you're doing a full field model that goes back 50 years, and let's say there's not a lot going on then, and you might have, yearly time steps then. You could, just so you get the material balance right, and then you refine it. Okay, then we have what we call numerical steps. These are smaller steps typically selected by the simulator to ensure convergence within acceptable error limits. So if there is a non-convergent time step, remember I said you took too big a bite of the apple? Well, what do you do when you try to take too big a bite of an apple? Well, spit it out, or you stop, and so the simulator will do exactly that. It will, if it doesn't converge, it doesn't just stop. It just says, I couldn't find a solution. And then it chops the time steps back, and different simulators will have different algorithms for that. But they do certain things. Like the first thing it might do is might chop it in half. And so let's say you try to go 30 days and there was too much going on and then it didn't converge. And then the simulator will automatically chop it in half and try then to go 15 days, from the previous one, 15 days, and then maybe solve it. And then it'll build up it'll start to build up the time to, let's say it chops it to 15 days. And then it won't go another 15 days. It's already chopped once. So it might go, 3 days or 5 days or something like this. And the simulators will have the algorithm to do that. Now you can control aspects of these decisions, but the engineer frequently doesn't. Let me see if I can show. I'm looking at the, okay. I don't know if you could see this or not, but we'll see. So let's. Okay. Let's say our report time steps are 1 month. Okay, so these are 1 month. So this is January 1, and then this is 1 March. Now I don't normally do. Well, you could do that. It's easier than changing the days. 31, 30. But so let's say these are the report steps, and if your model is well behaved, can you even see that, Jessica? Nod your head if you can see that. Great. It's yeah.
We can,
Anyway.
we can online, we can save, but no problem.
Okay, so look at where my hand is going. So if the model is well behaved, it'll solve 1 month, 1 month, 1 month, and it'll be fine. Okay, now every once in a while, it'll come to a place where, and so remember, we're telling it this, and we want output then. And then you have a whole bunch of control on the output. You could have it print to the print file. You could have it exported to a separate file where if you want to look at saturations through time and stuff like this, you'll have this information in there. So you could look at these pretty plots with the saturations moving through time and whatnot. It will save, let's say you want to know oil saturation or pressure or porosity, you can change it, that does change through time sometimes. You can have that output, and if you wanted to see it in the 3D displays, it will save a value of porosity for every grid block. So if you have 500,000 grid blocks, you'll have 500,000 size. So you can put that in the print file, and the print file is what we used to print it. Nowadays, you probably don't print it, but you can look through it and read it like text, right? Or you could have it export to what we call it's a binary file, but it could be, sometimes we call them restart files, but it's a separate file that the results viewer uses that file to plot, right? But if you start printing off all that information for every time step, we're talking about gigabytes of data. I mean, it's a lot, can be a lot, and it'll fill up your storage pretty quickly. So you might end up doing this for the reports, but then maybe every year or every quarter for the other. Okay. But then let's suppose it goes and it tries to solve it, it can't. So it can't do this. And so then it'll cut a time step, and it might cut it in half. So it'll go like this, and then like this, and maybe it solves it fine. But if it cuts it in half and it still doesn't solve, or it doesn't solve it, then it might cut it by a 10th, or by multiply, cut it 90%, right? So then it'll do this, and then if it solves there and it better, and by the way, sometimes it comes to a screeching halt where it's almost real time. It'll be, it'll be seconds, and it's always in fractions of days, but it'll be in 0.0001 days, and then so if there's real difficulties. So then it chops it, and then it'll try to go a little bit better, and then a little bit better, and then it'll stop here. It always is going to stop where you tell it to stop. It's always going to have a time step where you tell it that's that report steps. It's reporting the output. Okay. So let me just say one thing. If you have it, and you could, by the way, plot time steps, and this might be 30 days or something like this, and this is in days. And so you might, and let's say it's a monthly model. You could do this and then find the point that all of a sudden it drops to near nothing, and then it'll get back up again. Okay, so you can see if your model takes, let's say, 5 hours to run, but you're thinking, well, wait a minute, it's trucking along fine. Well, you might look at this and you might find all the, 3 of the 5 hours are 1 week of time. So then you can go back and do something to fix that. And one of the things you could do is, so you have monthly report steps, and the engineer could also, there's a keyword called T-steps or time steps or time, depending on the simulator. And you could say, look, I don't want you to take a time step more than 16 days. So even though here's a report step of a month, and even though it might be trucking around fine, no problem, you tell it, I don't want you to go more than 16. I say 16 days because then you're basically chopping every month into 2 time steps. Okay. And believe it or not, that could actually, depending on your model, you could actually make it run faster because it never goes to this chopping step. So when it chops, it might chop and makes this one, 10 different time steps, depending on how far it has to chop back. And maybe all it needs is a 15 or 16 day and a 16 day. Okay. So just a general rule of thumb is if your model is having convergence problems, the first thing I would do is impose a time limit, a time step limit. You don't have to change anything else in your model. All you do is put a keyword in there and say, the keyword usually set up, well, after the keyword, what's the max T-step? And usually it's a small one. And usually start the model with a T-step keyword. So it'll start off with like a 0.1 day, just to get it going. And then the next one might be the maximum time step. And then the next one might be the maximum cut or something like this. You have to look at the manual for that. But what I'm saying is if you have a model that is having convergence problems, the fastest and easiest thing to do is put that one keyword in there and limit the time. And I just said 16 days, right? If that didn't do anything, change it to 5 days and then see. But you could also use this with the plot of time step and you could kind of balance it. And so if most of your model is running at 30 days and there's just only a few places that's a problem, well, you could put that T-step keyword, you could put the T-step keyword, you could put multiple T-step keywords in there. And you could put it there and say, okay, I want you to just take daily time steps until you get through that crunch and you're back to normal again. So it's a real easy thing to do. You don't have to change anything with the model except that one little time step. Okay. Okay.
Professor, maybe I mixed it if you have talked about this earlier. So what are we trying to achieve by changing these time steps?
You're giving the simulator, you're not advancing the simulator to a point where the change in the saturations and pressure are significant enough that the simulator can't converge. So basically you're taking smaller bites at the apple. Does that make sense? You're muted.
Yeah, somewhat.
Okay. Okay. Well, I think you might see it when we're doing our models, but basically all we're saying is that there's some points in time in your model where certain things are happening that the time steps might be too big. And it really depends on what you select as your time steps to begin with. If you have yearly time steps, that's, and there's a lot of things going on, that might be too big, even though that you only have data that's tabulated by year. So you might have to take, the rates might be the same, but you might have to take smaller time steps in order for the model to converge.
Okay, thanks.
They don't have to be. So you could, again, it depends on the data. So as I mentioned before, if you had a full field model, and let's say it's 50 years of history, you really don't care much about the early stages, you could make them yearly time steps. And I've done this before. You have, let's say, yearly time steps for the first 10 years. Let's say there's only one well and nothing much going on. You could have yearly time steps and you crank through those, and then you start to go, let's say, monthly time steps or quarterly or something like that. Well, okay, so I think that could be a good question. So whenever we talk about rates in the model, it's always barrels per day. So it's independent of the time step. So it's always a rate as opposed to a volume at the end of a time step. Okay, so summarizing on the theory of simulation, it's important to understand the process. Most of the theoretical issues discussed here are transparent to the use of the robust commercial or in-house simulator. I'm telling you, the only time I see this is when I teach it. and there's a lot to it that I don't know. It's just, and guess what? I don't need to know it. It's kind of like driving a car. you know, it's nice to know how the carburetor works, or if you have fuel injection, it's nice to know how that works, but do you need to know it to drive the car? No. Maybe if you're pushing it to limits or whatever. When in doubt, consult the user manual or contact software provider support desk. All these things that I'm talking about here, there was a day, time and place where these were important for you to understand because you had to do things to make the simulator run smoother. But now they've done a really good job optimizing it for you. And like I said, these time steps, you generally don't have to worry about that. But you can, and you can control that. So. And again, if you have any, and we'll talk about errors here soon, but if you have any issues with the model running, the actual model running, you could always call CMG and say, my model is having problems and here's what's happening. And they'll usually say, send me the last line, because usually before it crashes, it'll tell you something about what's going on. But we'll talk about that. Not today, we definitely will next time or time after that. So let's just compare some of the software packages. So, and you know, this might be out of date. VIP use a core for initializations, others do not. Hardly anyone uses VIP as I know it today. Units, always check your units. So for example, when you're building your PVT section in Eclipse, Eclipse likes to use MSCF, thousands of cubic feet. CMG wants things in SCF. So GOR and stuff, you can't just take it, put it in there. You have to make sure the units are correct. Well, if you use Builder, it'll make sure you got the right units, because but I usually, and we're gonna be working with the input files directly. And so I usually like to have the comments in there, comment cards. We'll talk about that, and then have the units in there. So you have a record of what the units were or what they are. So if you're going to convert that, so, oh, okay, now I understand why all of a sudden I have, you know, crazy in gas in place or crazy small oil in place, or whatever it might be. Some simulators have features that others do not. Like, let's say most simulators have quarter point geometry, and we'll talk about that when we get into gridding. Things like threshold pressures, robust dissolved gas in solution, rock and compressibility compaction, so it's changing porosity and permeability through time due to compaction. Threshold pressures means you have a fault and you have you can have a threshold pressure at which the delta P will build up to a point, and then all of a sudden it'll start to flow. We've seen that happen, you know, you know, when you deplete one fault and all of a sudden the faults talk to each other. They don't at the beginning. So some simulators have that, some don't. Some packages have more features included, while some are considered additional add-ons. And one example that I tend to use, and one of these days I'm going to be wrong about it, but I think it's still right, and that is like local grid refinement. We'll talk about that, but local grid refinement it's built into CMG, but it's a cost add-on for Eclipse. So there's certain things like that that some of them include it, some of them don't. So when we edit the model files, the data files, whatever you want to call it, most of the robust simulators, and certainly CMG is one of those, will have a separate piece of software that helps you build the model. It makes it easy. You don't have to have that. You could look at the manual and here's the keyword and I put it in there, but this makes it a lot easier because it checks the data for you and whatnot, and then it stores it in the right place in the model when you're building the input file. You can use a common text editor, but let me explain something here. Does everyone know the difference between this here? This is the same data, by the way. Does everyone know the difference between this one and this one? I mean, is there anything that's, huh? Oh. This one and this one.
Yeah, one is well arranged, the other is not.
What we say it's well
arrangement. This is the one to the left is well arranged. It's neater.
Yep.
The other to the right is kind of rough.
And that's the answer I was looking for, actually. So the one on the left, basically you're saying they're nice columns. And the one on the right is not. And so and it's exactly the same data. The only thing that's different is in this one, I used a non-proportional font, which is Courier. Courier, it's the old fashioned typewriter font. But the reason why we like to do that, I like to see that, and I asked for it, is because then everything's all in a nice column. If you have, it doesn't look so bad here, but so in this one, you can't see, but this is oil viscosity, for example, and it's a nice column, you know, that's all oil viscosity. In some cases, this thing gets so jumbled up, and so it's not in the right column. And all you do is like when I ask for an input file, an input deck, which you'll provide, make sure it's in Courier font because everything lines up and is perfect. And it helps you when QCing, or it really will help you later on when you wanted to go in the model and make a change to something. Okay. And then let's see. When you submit the model, and we'll get into this a lot more, but when you, bless you, when you build your input file, it's basically a set of instructions that the model is going to read, and then it will, or the simulator will read, and then it will start its calculations and do its thing. You could submit these cases. In other words, you take the input file and submit it to the software in different ways. And in some cases, you could just highlight the case and this, or go to a text prompt and then give a certain set of instructions. The CMG has a nice scheduler that once you generate the input file, you could drag and drop it onto IMAX, the IMAX icon. You don't know that. I mean, you haven't seen that software. Has anyone used IMAX before? No? Or Eclipse? Okay, well, you'll have this when you get the software loaded on your machine, you'll drag and drop and it runs. Or if you want to run a couple overnight, there's a schedule, and so you line them up and tell them do this one first, and when this was done, you do this one. You always want to check the print file. So the print file is when the model runs, there's a couple files, and we'll talk about that in a little bit, but when it runs, it generates several files. One's a print file, one's a restart file, which we'll talk about that later, and one's a file that is read by the 3D visualization software. That tends to be a large file, so it's a binary file, you can't read it. But the print file, or the out file for IMAX, is where you go in to look at things like what's the production at a certain date, or what's the material balance error, or you want to see certain things that happen during the run. A lot of times that will be the same information that scroll. If you submit it a certain way, it'll scroll across your screen as it's running. Sometimes it's that output that goes to the print file. It doesn't have to be, but you can set it up that way. So it's basically a log of the run. What scrolls on the screen is the log of the run, and it tells we're at this time step. But some of the results aren't put in there, but the results will be in the print file. So pre-processing, things like for IMAX, which you'll use or can use, is Builder, and it basically queues you for everything that you need. Like it might at the start of it say, is this black hole amount or not? What's the dimensions? Those type of things, and it'll prompt you for that. Post-processing, so pre-processing obviously is what you do to build the model before you run it, and then post-processing is after you run the model, what do you do with the results? So IMAX has what we call results and results into 3D, and I believe the latest software combines them too. I don't think there's a results and a results 3D. I think it's just results. In Eclipse, it was Office and Graph and FlowViz. So you had different modules to, if you wanted to do XY plots, where let's say it's like a decline plot or a production plot. You could, and we'll go into this probably next time. You can look at production versus time. But if you want to look at the structure and look at the colors and look at that moving through time, that's the result 3D. So, but I think they're combined in the same package now. The 3D visualization, it's very useful because it conveys a lot of information quickly, and you could look at it quickly to say, oh, okay, where's gas coming out of solution, or where's a secondary gas cap developing? You're not going to really see that if you just look at a bunch of numbers on a page, but you will see it very easily, and it's a way to check the model quality and the interpretation of what's going on. You can QC large amounts of data. One of the things that you could find if you input, let's say, porosity wrong, it's going to not look natural, and you could see that real quickly, which you never see it, you know, if you didn't look at it in the visualization tool. You could check the model performance for unusual activity, like let's say you have a fault block that's depleting that you thought it was isolated. Well, you could look at pressure and see where the pressure in that fault block is depleting, and find out, oh, there's a misdescribed fault in that area, and you go in and then you can fix that. And then convey concepts to management. A lot of times if you're presenting the results, let's say you want to show a water flood that's more effective, well, you could show the sweep of the water. So it's a very good tool. I encourage you, especially in Project C, to use some of the visualization tools that you have. Sometimes people don't do that. Case naming conventions. It's all we're talking about here is what are you naming your model, Rod? Okay, and so a lot of times you typically wouldn't say model 1 or model run 1, model run 2. Usually there might be a change that you're making, or you're focusing on something, and let's say it's compressibility. So you might say, you know, HM, if it's a history match, HM001 underscore perm, or compressibility comp. And then if you wanted to submit some overnight and you want to do a range, let's say a bracket of, let's say 20% low, you know, 10%, well, you might submit them all at the same time and call it, 10 low and 20 low and 10 high, 10, so you're going to name these files something that will help you remember in that particular series what was important. Because you're gonna go through this process when we talk about history matching. You're gonna go through this process where you work on one thing, and then you're going to work on something else. You're going to work on something else. You're going to work on something else, and you're not working them all at the same time. But you get comfortable with something first, like let's say aquifer size, and then you start to move something, and then you're gonna have to go back. So it's a good idea to name them properly, and I'm going to show you about documentation in a minute. Some use the date of the run. Some use very descriptive names. Some of them, they're way too long. Use a system that works best for you, but always keep backups for your data files. So the model files themselves are pretty big. Particularly the grid files are fairly big, because there's going to be, depending on the nomenclature you use to define the grid, there could be three numbers per, or three per grid block, or it might be like 8, maybe 16 items per grid block to define the structure. We'll get into that later. But the point is, the grid is a very large portion. Sometimes the tubing tables are fairly large, but the data deck itself is fairly small. So I usually just, every run, I save that data deck. You save it, because there's going to be a point in time that you're kind of going in one direction, and then say, wait a minute, this model doesn't look as good as the one that I had yesterday. And you might have to go back to the one yesterday. So it's always good to save those data files. Never just write on top of it and then on top of it. You don't want to do that. You want to always keep them. It doesn't take up much space at all to have a little. I usually have a directory called like dat save. And then whenever I do a run, I might blow away the results, but I keep the dat file in there. Because sometimes there's, you'll be going along and then you won't realize, and all of a sudden, let's say the model run time is double for some reason. And you just didn't realize it. I know that sounds crazy, but it happens. And so you want to go back and find out where did that happen? And what did I do to the model to create that? And whatever I did in the model, was it a material change? Or could I get by without it because I could save my run times? So, and I'll show you an example where you want to keep track of the CPU time. But always use a different file for a different run. That's basically what I'm saying there. So documentation. So every modeling project, simulation study should have a final report, at least a letter summarizing the final results. It's always good practice when you're history matching to keep notes of what works and what doesn't work. Because there'll be things that will help the history match, and there are things that it just doesn't matter. So you want to write that down, because we're talking about a lot of different parameters that you could change, and you'll forget. I forget, but you'll forget. Say, wait a minute, did I change compressibility? Did I try this or that? And maybe at that time it didn't matter, and maybe at this time it still doesn't matter. But at least it'll be helpful to go back and check your notes on that. Keep track of the models run and the changes to the model. So, for example, I like to keep a log where the date is the day that you're running making that run. What's the run name? And let's say it's HM001 underscore, new wells or whatever. And then a small description, right? New infill wells added, back in 2003. And then the prior model. So when you're doing this, you're going to take a model, a data file, and you're going to copy it to a new data file. You're not going to, you're going to start, it's a process it's a story that you're telling, and you're going to start with something that and then you make a copy, and then make one little change in that model, and then you continue on. So it's always good to sit and say, which model, because it's like a tree branch where you might start with HM001, and then you start to worry about the compressibility, and you like it, and then now you're worrying about aquifer porosity, and then now you're worrying about something else. So it's a tree, and then each of these might have like 5 different runs, and you pick this one, and then you went from this one. Okay, so you want to keep track of what the name of the model run was, and what was the main difference that you had in that model, because it'll help you during your history match process. And remember, depending on the project C, some teams ran the model 300 to 500 times. So you're not going to remember. I mean, if you are, you're brilliant, but it's going to be very difficult to remember. You'll remember some generalities. You'll remember that, I remember we changed the rock compressibility, and it made tremendous improvement. But you're not going to remember whether it's 30 microsips or 10 microsips. Well, and then runtime, it's always good practice to keep the runtime. That runtime will be at the bottom of that out file. And usually it'll say 2 things. It'll be a CPU time and a elapsed time. CPU time is if you're fighting, you're using a computer and others are using the same computer, well, that CPU time will be different than the runtime, because that's CPU is being swapped out by other folks using that particular computer. I think you probably have dedicated computers on your models. It's all you're running them on your standalone, so your CPU time is going to be very, very close to the runtime. So you want to keep track of that. Like I said, the models that we're using in this course they'll run in less than a minute or 2. But if you're running a model that takes 3 hours to run, and then it crept up, you don't know. I mean, there's sometimes all of a sudden you change one little parameter, and it changes the runtime dramatically, and it didn't help. And you might have said, well, it helps a little bit, and you stay with that, and then you forget that, oh, that actually doubled the runtime. So why stay with it? So you want to run that runtime, and then original gas in place, original oil in place. It's also good to keep those, especially the oil in place if it's oil fill, because you remember the original oil in place. Hopefully, when you initialize that model, it matches with what the geologists and geophysicists had. Well, you might change something a little bit. Well, I changed the porosity, or change this, or by accident change something that you didn't think. You might see it in that original oil in place, and so you keep track of that to remind you, okay, we're still in good shape. Okay, well, we made it. So, by the way, any questions on this or lecture 1? Has anyone not been able to find, if you were looking for it, the lecture 1 recording? Anyone having a problems with that? I think everyone's all on Blackboard and now we're all connected with the 2 sections. So, so next week, I will have a gentleman from my office run through. He's basically going to, I think, show you how to do Project A, but he's going to go through a set of instructions on how to build a model, and he'll be using CMG, and he'll also go into the results viewer and how to look at the results and stuff. Basically, it's a quick tutorial on how to use the software. Well, that's what we did last time. That's what I plan to do. Now, I warned him that he was going to be, he's volunteered for this, but I think he's got COVID right now. I shouldn't say that. I think he's out sick right now. Yeah, I actually, I think it was last week. So he's probably going to be fine, but I have the recording from last year. So if for some reason he doesn't, I'll just play last year's recording. And then either next week or shortly thereafter, I will start to send you some information for you to send CMG information about your computer. So they could send you a license file that will be tied specifically to your computer. And we may, Project A, I don't think I assigned that for, I don't know, does anyone know when I signed? It's not next week, and it's probably not the week after, but it might be the week after that. And does that sound right? Okay, it's in the syllabus. So I'll make sure it's always the case that that you guys will have your, let me stop the recording. I guess it doesn't matter.